So we had to reschedule a bit. So the first superwoman is Josie. And where robots learn from the best teacher, of course, from Mother Nature herself, of course. And so Josie will reveal the secrets behind designing robots that can interact with their environment in ways that are both clever, robust, and sustainable. And directly with my favorite fruit, raspberries. So let's taste from the research of Josie. Thank you.
Excellent. Thank you very much, Bram, for the introduction. So there's one thing we've talked a lot about at this conference, which is embodied AI. But I'm going to talk a little bit more about how can we actually use this embodiment for AI and how do we design the body. And for this, with my group, we've been really looking and taking this approach of embodied intelligence, really formalized by Rolf Pfeiffer, Famir, and others in this concept. And to me, this embodied intelligence is really about providing intelligence and computation from the body, offloading cognition to the body. And we see this across biology, through even reflexes, the use of compliance, the use of morphology for sensing. And this, to me, is just a beautiful, beautiful explanation and demonstration from biological systems of how we can achieve speed, self-organization, robustness, all these parameters which we want our robots to have. So I'm driven by how we can learn from biology, taking these principles of embodied intelligence to design robust, physically intelligent systems. But how do we do this? How do we learn from biology? So if we look at biological systems in contrast to robotics, there's something we see about the physical complexity. We see a huge range of material stiffnesses used. We see different morphologies from cells to orchestrated structured processes and organizations such as organs. And we also see that biological systems are constantly evolving. They have a time scale, they have a temporal aspect that we perhaps do not see in robots. So I believe we need to increase the complexity of our morphology, our range of different stiffnesses, how they're distributed through the body, and also the temporal behaviors. So I'm going to talk a little about these three principles and some of the ways we can use these to divide and to create intelligent robots. Starting first from morphology and passivity. And I want to start from another, I think, beautiful example, is this which was identified by Maxwell. And he saw, if I have different round disks and I let them drop, they will fall in different ways. We can essentially encode some kind of behavior and some kind of controllability through morphology in paper. And we looked into this a little bit with robots to do large-scale data collection to kind of identify different patterns of behaviors. And I think this is really interesting, how we can have a direct representation of how morphology can encode behavior. With one of my students, Nana Biashi, she talked this a little bit further, and actually, again, can we build probabilistic models of paper aeroplanes? Can we program behaviors, in this case a trajectory, purely through morphology? And indeed, we can. We can use large-scale data capture methods and develop programmability of morphology. But this can only take us so far. Unfortunately, a paper plane is not going to solve a lot of the applications we have. But what about if we take the morphology, and then we add some, keeping it a passive system, adding some stiffness distributed through the system, adding some connections between them. So we've been looking at co-designing the morphology, stiffness, and tendon routing, incorporating stiffnesses to go from a required kinematic data set into a robot, which is completely brainless. So you may have seen the passive dynamic walker. This is our passive dynamic half dog. With zero brain, by having the correct kinematic chain, the distribution of stiffness, and tendon routing, we can achieve this robust behavior. There's robust perturbations, very rapidly recovers without a brain. And this gives us some illustration of how we can then build intelligence on top of this. But of course, with locomotion, the form factor of the morphology is largely fixed. But if we look to manipulation, I think it's still very much an open question. What is the right form factor? What should the ultimate general purpose manipulator look like? And should it be a human hand? So we've been looking at creating an open parametric hand, which is a design with, I think, 52 parameters. We can represent a wide range of different hand designs. This can be single printed, and we maintain the passive properties of joint behaviors. And we combine it with synergistic actuation units. With this, we can express a wide range of different hand morphologies and really investigate the role of morphology in grasping. But still, here we only introduce a single actuator. So for example, we could have a full scale hand, a mirrored two-thumb hand, or a primate-inspired eye hand. And with these, we can see that this morphology can significantly affect their operational capabilities or advantages. For example, we see the human hand has very good lifting capacities, whereas the two-thumbed hand opens up new opportunities for grasping modalities, or finally, an eye hand is very good for actually clinging onto trees. So compliance here is very useful. We have morphology and we have compliance. And in soft robotics, we see compliance is really widely used, but often in a monolithic form. I think directionality and location of this stiffness is really important. So that's the second thing I want to talk about. And if we talk about an upper limb or a hand system, a lot of our compliance is in joints, where we constrain the direction of the stiffness through ligaments or bone joint systems. So how can we now not just have compliance, but control the direction and distribution? And like many working in soft robotics, we've been working on trying to come close to some of the capabilities of an elephant trunk. And to do so, we've developed this soft robot arm. But the innovation here was really looking towards directional stiffness and creating what we're calling, or is called architected structures, where we can use the geometry to decouple our ability to define the axial and bending stiffness. This allows us then to design robots that have the operational range, but also the controllability and the compliance to show some of these capabilities we have with soft arms. But of course, we still need the control and sensing approaches. So we're looking at developing methods that can deal with continuum deformation and combining these with online sensing methods, such as here, we're using IMUs to have real-time state estimation to have control with these structures. So arms are fascinating in terms of distribution of stiffness, but I think one thing that's come up a lot in this conference is manipulation and hands. And again, if we look at the distribution of stiffness in here, from the skin to the finger joint, to the wrist, we see there's an increase in stiffness as we build up and go higher in this hierarchy. So we've been looking at, can we develop a robotic system where we match the stiffness of this skin, joint, wrist stiffness to that of a human? And the idea, but this gives us a hierarchical kind of robustness at different scales. By developing this, but also matching the kinematics of a human, so we now have a robot hand, the adapt hand, as we're calling it, that matches the stiffness distribution and the kinematics of a human, we can have one-to-one teleoperation, which not allows us a very fluid interaction and to show new capabilities with these hands, but also we can use this teleoperation to teach new capabilities. So we're looking at combining this with a fine-tuned OpenVLA model and a low-level diffusion policy, but teaching very human-like skills. For example, error recovery. How we can actually recover from failures, just using visual information, or even environmental constraints. Can we actually use and exploit the environment to pick up objects and choose the grasp type depending on the environment? So the last thing I want to talk about is temporal adaptation. If we look at animals, we constantly have different timescales of adaptation, from shape-shifting, reconfiguration of bodies, and of course, growth and development. And the nice thing about robots is we can have this temporal adaptation without being limited by energy, time, or reversibility. So we've been looking at this for morphing robots. So this is our wire mesh kind of morphing robot that has onboard tendons. And this can morph from being a flat structure to a ball, by defining, again, the stiffness of these structures correctly. This allows us to then adapt to different terrains, to exploit the body in different ways, and also to exploit morphing to escape and overcome from obstacles. So, to wrap up, I believe we really need to scale up the complexity of our robot bodies by using morphology materials, considering the stiffness distribution and direction, but also temporal adaptation. So, just a brief advert before we finish. I would really encourage you to consider submitting a paper workshop application to Robosoft 2025, which is another RAS conference to be held in Lausanne this coming April. And of course, I also want to take this opportunity to thank my fantastic lab who've undertaken all this fantastic work. I'm so lucky to have you. And finally, I think it's just really important to say, I think it's just such an exciting time to be part of robotics, and just what a fantastic community to be part of. So thank you for listening.
I was very smart not to propose €5 for being on time, because I know all the next speakers will be very punctual. Are there questions? Was there? Yeah, sorry. Yeah, please, there.
It's becoming a theme. Great talk, Josie. Thanks so much. I think a lot of us agree that adding compliance is really interesting. It also comes with its own challenges. For instance, you show some tendon-driven systems, which obviously adds its own complexity in terms of modeling and control, and et cetera. So I guess I was just curious, how do we balance those two, and maybe your perspective on how to, you talked about it a little bit, but a little bit about how to, especially for tendon-driven devices.
I think tendons are a great way forwards until we develop artificial muscles and other soft actuators that can really behave more like biological systems. They come with their issues in terms of friction and tendon routing, but I think they're a great, we can solve engineering challenges to use tendons until we can then actually have more muscular solutions. So I think we really need to push on the actuator side such that in the longer term we can move away from actually having long Bowden cable-driven tendon systems to get around this. But yeah, compliance, it's a mixed bag, and it's exciting to have these challenges to work on.
Great, good talk.
Okay, thank you. Then we can go to the next speaker.